Okay, hello everybody. So this is going to be the last lecture for chapter 5 and the last lecture of material that's going to be on exam 1. So what we're going to do is we're going to keep talking about uh, stereoisomers. We're going to talk a little bit more about diastereomers and talk about some of their physical and chemical properties and some of the ways that we represent these compounds as far as how we would draw them and how we would name them. So let's start off with a question, which is which isomers of 1,2-dibromocyclohexane are chiral? Okay, so if you go and draw this compound, the first issue that you're going to notice is that the two bromines that are at the 1 and at the 2 position, well, those can be drawn in different orientations. So, for instance, I could draw the two bromine groups like trains, so one up and one down. But if you think about that for a second, and you draw the mirror image of this compound, which is also a trans 1,2-dibromocyclohexane, you're going to quickly see that those are not really acceptable names because, well, those are two different compounds. So two different compounds that are mirror images of each other but are not superimposable. So everybody recognized that if you were to take this compound and to rotate it around so that the bromines were on the same on the right hand side, that this bromine would now be pointing down and this bromine would be up. And so that is clearly a mismatch here for those. So the relationship between these two compounds here, which I'm going to call this compound 1 and this compound 2, these two compounds are enantiomers. Now, the way that you would name these compounds is you would need to use the RS assignment to do that. Okay, so what we're going to do is we're going to go through and we'll do this kind of stepwise based on what we're talking about. I'm going to show the hydrogen atom here. So obviously the bromine here is our number 1. And then coming over here to this carbon, this is going to be our number 2. And this is going to be our number 3, and our number 4 is already pointing back. Okay, so the rotation here is 1 to 2 to 3, so that's going like this. That is a clockwise rotation, which is R. Okay, and so then I want to be thinking, all right, check my number 4 group, everything is at K, and so I'm going to assign that position as R. Okay, now if I go down to position number 2, this bromine is number 1, and then carbon here number 2, and this position number 3. And if we do the rotation there, we've got 1, 2, 3, so that's going this way, so that's counterclockwise, so I think S. And here I need to check my number 4 group, which the hydrogen now is pointing up. Okay, so that means I need to give this opposite assignment, and so that means this center is going to be R as well. Okay. Now, my question is based on what we said last time, what do you think the configuration is going to be of this compound right here? Okay, now we'll just go ahead and name this one since we went through the trouble of finding all of this. And so the way you would do this is you would say 1R, 2R, parentheses, dibromocyclohexane. Okay, so that pretty much nails it down. Now, is it chiral? Well, it has a mirror image that's not superimposable, so it doesn't have an internal mirror plane. So yes, this is chiral. This will most certainly fall into the category. Now, what do you think the configuration is going to be of these two centers right here? If this is our, let this be our number 1, and this be our number 2 here. And if you say, well, those should be the opposite configuration, you would be correct. So if you quickly look at this, so here's the hydrogen number here. So this is 1, this is 2, this is 3, going like that. That's counterclockwise S. When you check your number 4 group, it's back, and so that means this center is in fact S. Then if you come down here to 2 position, you've got bromine 1, you've got this carbon 2, and this carbon 3, and so it's going 1 to 2 to 3 like that. That's a clockwise rotation, which is R, but your hydrogen down here is pointing towards us. So that means we need the opposite configuration, and there it is, in fact, S. So the name of this compound here is, in fact, 1s 2s dibromo cyclohexane. And that's not a mistake. Okay, so the mirror image, the enantiomer, should have the opposite configuration at those positions. Now, there is a third possibility here, and this is also a chiral compound as well, because it has a mirror image and it's not superposable. So both of those are chiral molecules. But there's a third possibility here, and that one is, of course, if the 2 bromines are pointing in the same direction. Now, we talked about this last time, that if there were an internal mirror plane in the molecule, meaning you fold one side over the other, that would immediately mean that the molecule is not chiral, or as we would say in the business, achiral. Okay, so this is not a chiral molecule. But we could assign the stereocenter positions here, just like what we did up there. And so we already know that that stereocenter position from up here should be R. And based on what we did earlier, okay, what do you think this stereo position is going to be down here? Okay, so we check that 1, and 2, and 3, and you're going this in this direction. So that is a counterclockwise, so that's S. And the hydrogen's back, so that is in fact S. Well, isn't that interesting in that you see an R and S mirror? Goodness, I'm sorry. There we go. So you see an R and S mirror here between those 2 centers. I apologize, I've probably talking for 2 minutes, but you see it now. And that is in fact means that this molecule is not chiral. So you could go and name this compound, and you could say, okay, this is 1R 2S dibromo cyclohexane. But there is another name that is more common, and the name that you'll often see in place of this is meso 1,2 dibromo cyclohexane. And what that meso indicates is this is telling you that this is a compound with stereocenters but is not chiral. Okay, so compound with stereocenters but is not chiral. So this third possibility here is interesting, okay, because that's a molecule that, you know, if you try to draw its mirror image, it's going to be the same molecule, okay? So it would end up being the exact same thing. So if you drew the mirror image of this system, it would end up being this, which is in fact identical to that. So if we label this compound number 3, okay, right here, compared to 1 and 2, what is the relationship between 1 and 3 and 2 and 3? Okay, Do they have any relationship at all? Well, let me start off by asking you this question. Are they configurational isomers? Meaning, do they have the same connectivity, okay, but are different? And well, yeah, the bromines are in the same position, but they're just oriented differently. Okay, so they're definitely configurational isomers. But are they enantiomers? Well, no, because they're not mirror images of each other. So what is left over if they are not enantiomers? Well, that is in fact what we talked about last time. We would classify these as diastereomers. Okay, diastereomers are configurational isomers that are not mirror images of each other. In other words, they're not enantiomers. Okay, so that means the relationship between the two trans compounds, the 1R and the 2R, the 1S and the 2S, and the meso compound, is that these are related to each other as diastereomers. Okay, now diastereomers are interesting in that you don't have to have necessarily a stereocenter to fall into this category. Okay, in fact, you can have molecules that are, well, technically not even chiral, okay, and fall into this situation. So for instance, if we looked at this compound, all right, that is trans 1,2-dibromo ethene, excuse me. And we looked at this compound, which is cis 1,2-dibromo ethene. Well, those are not mirror images of each other, but they are configurational isomers, meaning they're put together the same way. They've got one bromine on each side and they have a carbon-carbon double bond. So these are compounds that we would classify as diastereomers. Okay. So this is kind of like diastereomers and enantiomers have very different physical and chemical properties, which is what we're getting ready to delve into in just a minute. But what I want to talk about right now, before we get too much further off track, is I want to mention another way that we can express chiral, or we can express, compounds that have stereocenters that may or may not be chiral. And that is by looking at what are known as Fisher projections. Now, those of you who are going into biochemistry are going to see a lot of this stuff. So in 1840, okay, I guess this is where this story starts. Louis Pasteur, okay, separated enantiomers of tartaric acid, which is found in wine, by hand. Because he actually had some tweezers and he was able to separate the crystals out. And some years later, in 1890, Emil Fischer, who these projections are named after, classified enantiomers of carbohydrates, which are sugars, using a novel method of structures with perpendicular lines. Okay. Now, the way that these work is if you have a tetrahedral center. So let's say we have this compound here, A, B, C, D. That's a tetrahedral center. And you view that, your mind's eye kind of looking straight head on so that C and D are coming towards you and A and B are going away from you. All right, that gives you a representation of something that looks like this. Okay. And the way that Fisher projections work is they basically imply that the groups that are pointing on the top and the bottom are pointing away from you, and the groups on the sides, to the left and the right, are coming towards you. And so that is essentially simplified down into just drawing it in this manner. Okay. Now, these are used, like I said, a lot in biochemistry to kind of represent carbohydrates, and I want to mention a couple of examples right now. We're not going to get too overboard in this because you're going to see this a lot in biochem, but let's go ahead and look at tartaric acid. So here is one form of tartaric acid. Here is a second form of tartaric acid. And here's a third form of tartaric acid. Okay, now, if you look at these, you can see, all right, that the carboxylic acid groups are, kind of groups that are going away from us. The ones that are coming towards us are these two OH groups and these two hydrogens. Now, it should be pretty easy to see right now that these two compounds here, okay, compound 1 and compound 2, are not mirror images of each other. Okay, there's a mismatch right here. Okay, but yet they are configurational isomers. So the relationship between 1 and 2 is that these are in fact diastereomers. Okay, but if you look at the relationship between 2 and compound 3, okay, you can clearly see that those are mirror images of each other. And so the relationship between 2 and 3 is those are in fact enantiomers of one another. And if we went and compared compound 1 with compound 3, okay, those are also not mirror images of each other. There's a mismatch right here at this position. So those are diastereomers of each other. Okay. Now this classification is going to be important in a minute, okay, because it means that that tells you something about the chemical and physical properties of these compounds. Okay, now are any of these compounds chiral? Are any of those compounds chiral? All right, and if you said yes, you are correct. So compounds 2 and compounds 3 are in fact chiral here. They are mirror images of each other that are not superimposable, and so that means there's no internal plane of symmetry, whereas compound 1 has an internal plane of symmetry and is not chiral, and we would classify that as a meso compound. Okay, so that's just again reiterating what we had just talked about. Okay, now let's take this one step further. All right, so let's say you had these two structures, these two Fisher projections, and you wanted to know, okay, what's the relationship between these two? Are these structural isomers? Are they enantiomers? Are they diastereomers? Or are they the exact same compound? Now, I've kind of muddied the waters here now because, well, now the top and the bottom groups here are in different locales. But I think you can see that the same three groups on the end are, in fact, the same, just in a different order. So that means we can eliminate structural isomers right now, okay? Now, the problem with Fisher projections, and this is again kind of, I personally hate Fisher projections just because it's not immediately clear, because if you see a three-dimensional picture, you know what it is. And so this is probably going to be one of our last times we're going to be talking about these in this course, but I do need to mention them to you since you are going to see them in the next class. The way that I typically handle Fisher projections is instead of trying to rotate the groups around, because they are not necessarily just, swapping one group for another. It's sometimes trickier than that. Is once I've ruled that these are now actually some type of configurational isomer or they're the same thing, I start to think about their configurations, their RS configurations. So if you come over here to this position and you say, okay, well, that oxygen there is clearly number one, and this carbon is double bonded to an oxygen versus a carbon that's single bonded to an oxygen and a carbon, well, this is going to be your number two. And that means this carbon down here is going to be your number three, and there's your hydrogen number four. Now you note that hydrogen number four is pointing, it's going to be pointing up, okay, based on what we just said. So you could do your configuration 1, 2, 3. That's a counterclockwise rotation, so you know that that position, that stereocenter is in fact orange. Okay, now you do the same thing down here. This is number one. Okay, that carbon is attached to an oxygen and another carbon, and this carbon is attached to an oxygen and a hydrogen. So that means this is our number two, and this is our number three. So if you connect those together, 1 to 2 to 3, you're going like this. And again, your number four group here is pointing up. So you're thinking S, but give opposite assignment as R. So this is going to be an R position. All right, now if we use the same tricks that we came up with before, I can figure out which one of these three this is. Okay, so let's just go ahead and do this right now. So this position right here, this is number one, this is number two, this is number three. So 1 to 2 to 3. That's going in a clockwise manner. Okay, so it's going a clockwise manner. So that means that you're going to think that this is R. Okay, and you're going to check your number four group, and in fact, this is this ends up being opposite, so this is going to be S at this position. Okay. And then down here, you've got your OH here's number one. Then you've got a carbon bonded to an oxygen and carbon versus a carbon bonded to an oxygen and hydrogen. So there's two, this would be number three. So we're 1 to 2, 3 like that. Okay. That's also going clockwise. Okay. So you're going to be thinking that is in fact altered. And now the hydrogen atom is, well, it's pointing away, okay, down here. So I know that this is going to be okay. So we're going to leave that as R. Okay. So I now know what I'm dealing with, okay. I've got an RR versus an SR. So that means one of the stereoisomers aren't matching, so they're not mirror images of each other. So the relationship between these two compounds is they are in fact diastereomers. Okay, now I know that that may not be exactly the same way it's explained in other circles, but I like that method because it's pretty ironclad. If I had found out that this was SS with the RR, then I know that's a mirror image. And if those two centers had both been R, then I know they're the same compound. So I like doing them that way because, well, it helps to reinforce R and S, and that's really useful, okay, in being able to not only name, but to also differentiate between isomers. Okay, now we're going to get into talking about physical properties of stereoisomers. Okay, and this is pretty wild stuff. So let me start off by saying that enantiomers have identical physical and chemical properties. Enantiomers have identical physical and chemical properties. So, for instance, if you look at this compound, all right, this is a compound, a natural product. This is known as limonene. Okay. And this compound has a related enantiomer that is also known as limonene. So the way that we differentiate them and the way that you can differentiate enantiomers in the laboratory is by putting them in what is known as plane polarized light. Plane polarized light. Okay. Plane polarized light is used to see the rotation of chiral molecules. It's used to see the rotation of chiral molecules. Okay. Positive rotation, okay, and negative rotation. So this compound, this particular limonene, it has a rotation of positive 11.5 degrees in plane polarized light. Okay, so it's designated as plus limonene. The second compound has a rotation of minus 11.5 degrees, and it's known as minus limonene. Now, these two compounds are obviously enantiomers of each other. Okay, so enantiomers will have equal and opposite rotations. Okay, they have equal and opposite rotations, but this does not designate R and S, meaning an R isomer can be positive or negative, and an S isomer could be positive or negative. You just know that the enantiomer is going to be equal and opposite of that. So this isn't a terribly useful technique other than to measure purity. Okay. Now, other than this method, the only other way that you can really differentiate enantiomers is through putting them in a chiral media, meaning you have to expose them to something that's chiral. Now, if you remember what I said at the beginning of this lecture, that we are made up of a particular set of amino acids. So that means we have an internal chirality built into us. So there are receptors, okay, that we have like in our nose that can differentiate between one enantiomer and another. So for instance, positive limonene is the smell of oranges, okay? And minus limonene is in fact the smell of lemons. And so those have very distinct smells. But chemically, those compounds really behave the same. They have the same melting points, boiling points, densities, elution rates, and IRs and NMRs for that matter. So it's very difficult to separate a mixture of enantiomers. So keep that in the back of your mind as I move into the next discussion, which is about diastereomers. Okay, diastereomers have different chemical and physical properties. Diastereomers have different chemical and physical properties. Okay, meaning they can be separated. In the laboratory, okay, fairly easily. You can separate enantiomers, but they generally require a chemical trick. Like you convert them into diastereomers and then separate them and convert them back to enantiomers. Or you have to use a chiral media to separate them anyway, and that's expensive. Okay? And I'm just going to kind of let the cat out of the bag right now. The pharmaceutical companies, a lot of the medicines that you take are actually mixtures of enantiomers, okay? And it used to be that, 50, 60 years ago, that it was perfectly fine or legal to sell pharmaceuticals to people as a mixture of enantiomers. The pharmaceutical company would just say that the other enantiomer was inert or, didn't really do anything. And of course, that was a cost saving maneuver. But this is not always the case. It turns out that the other enantiomer is often biologically active and does other things. Okay, so if you're familiar with the compound thalidomide, thalidomide was a medicine that was prescribed in the 1950s to women that had morning sickness, and it was a mixture of enantiomers. And it turns out that one of those enantiomers alleviates morning sickness, but the other one causes severe birth defects, okay, in the fetus. And so this was really a national tragedy when this happened, and so it caused truncated limbs in the children that were born. So there are much more stringent regulations, but that is not to say that everything is ironclad. Okay, drugs get recalled off the market all the time, and that's why it costs so much money to bring a drug to market, because it has to pass several clinical trials in order to actually be sold as a medicine. And in addition to this, pharmaceutical companies will often take advantage of compounds that are mixtures that of enantiomers, and they will separate them and test them each individually, which they're required to do. And they'll find actually that the mixture has as much potency or close to than the single enantiomer. And so what they can do is they can initially sell you a mixture of enantiomers, and then later on down the road, purify it and separate it as a pure enantiomer. And that's a trick to extend the patent deadline. So, most pharmaceuticals get about 7 years in the US where a pharmaceutical company can exclusively license a drug. And then after that, they kind of have to open it up to generics. But there's a lot of political and legal maneuvering, that is done with this. And the chemistry behind it is, pretty much this stuff right here, what I'm talking about. So there's a lot of ethical questions that we can pose here, and I'm not going to delve too far into that, but I want you to be aware of that. Turn bottles around and look at them now. Look for these positive and negative signs that you see on active ingredients. That now clues you in as to if that molecule is chiral and if there's an enantiomer associated with it. Okay. Now, all of that being said, there is a type of mixture that I want you to be aware of, which is called a racemic mixture, and we're going to see this a lot in the next chapter. And a racemic mixture is a mixture that's 50% R and 50% S, okay? And so no selectivity for one isomer or another. And it actually has a rotation of a racemic mixture in plane polarized light is in fact 0 degrees. And that's because half of it's rotating one direction and the other half is rotating equal and opposite. And so the machine adds it up and they cancel out. Okay. Now, achiral molecules will also have a 0 degree rotation, such as meso compounds will also not be able to rotate in plane polarized light. So, how do you measure the purity, okay, of a given compound, okay, and see, well, how much of a particular enantiomer is present in a mixture, like R versus S? Well, the way you do that is by measuring what's called an enantiomeric excess. And so that's just the rotation of the sample you're looking at divided by the rotation of the pure enantiomer times 100%. So if these two numbers are the same, that ends up giving you an enantiomeric excess of 100%, which means it's a pure enantiomer. But every time the rotation deviates in the sample from the pure rotation, it will never go above that number simply because the other enantiomer is going to be rotating in the opposite direction, and that's going to cause this value to decrease. So what would be the enantiomeric excess for a racemic mixture? Well, the specific rotation is going to be 0 degrees for your sample, and so that means that you're going to end up with a 0% enantiomeric excess, meaning R is not favored over S and S is not favored over R in any way, shape, or form. Now, let's put this in terms of a practical example. So based on what we were just looking at a moment ago with limonene, what if we observed a rotation of a limonene sample, okay, that was supposed to be enriched in positive limonene, and it had a specific rotation of 10 degrees? What would be its enantiomeric excess? Okay, so in that case, you have your observed sample is 10 degrees, and the pure enantiomer for positive limonene was positive 11.5 times 100%. And so this sample would be 87% enriched in the positive limonene sample, okay? All right, excuse me. So that gets me through pretty much everything that I wanted to say here about this topic. Okay, so there were a lot of things that were talked about here at the end that are very important as far as chemistry is concerned about physical and chemical properties of these samples. So we will be seeing a lot of this as we move into chapter 6 for the second exam. And so please, review this material, make sure this makes sense to you. And as always, if you have any questions, feel free to send me an email or post a comment in the comment section. I want to apologize also. My dog, I think, is about ready to eat, and so that's why she's got a little bit antsy. So with that said, guys, I will leave it there, and I will see you guys in the next video. Everybody take care, and bye-bye.